In this lab, we attempt to verify the energy principle by creating a computational model in VPython which mimics and compares the real-life movement of a mass on a spring, which was videoed and then analyzed in Tracker. From a set of initial data collected from Tracker and Newton's second law, we find the system energies and the sum of the change in system energy according to our choice of system, and find the total change in energy, delta E, is 0 for our computational model. This computational model effectively mimics the movement observed in real life, so we conclude that in this case the energy principle is satisfied. This lab is exciting because we can see that we can successfully predict real-world movement from nothing more than a set of initial conditions which are easily measurable and scientific principles such as Newton's second law and the energy principle. The spring model is particularly useful in attempting to model a system which has no outside forces on it, because springs don't lose energy to outside forces such as friction as readily as do many other moving objects. First, let's examine how we count the total energy for our system. The only thing significantly moving with respect to our experiment is the mass, so the kinetic energy is calculated for that object. We ignore the mass of the spring. Forces acting on the ball from the earth and the spring are counted as potential energies because these objects are inside our choice of system. Although we have undoubtedly neglected some forces that are affecting the real-life model, such as air resistance or heat transfer, these energy transfers were considered not significant over the short period of time we consider. These disparities in accounting may, however, have led to differences in the models which we will discuss later. We use the Tracker analysis to approximate the value of the period for both the x and y directions by taking an average of several periods. The y value is slightly smaller, likely due to its loss of energy through an imperfect spring action in the y direction. Movement is better conserved in the x direction, where pendulum-like motion occurs. The length of L0, the relaxed length of the spring, was determined by K sub s, and was then inputted into the VPython along with other initial values. These three lines calculate the various energies. Later, inside the while loop, we calculate the change in each of these energies for each time step delta t, so that for each time step we can find the total change in system energy, which should be, and is, 0. In this line we see where Newton's second law updates the velocity and position for each time step. Here are the lines of code which calculate and then graph the values of the various changes in energy, and finally a few arrows to represent the force vectors acting on the mass. In this model, I use the estimate for the period taken from the y values in Tracker. While the model obviously isn't perfect, it does a pretty good job of approximating the movement we observed in the Tracker, especially at the beginning. The discrepancies later on are probably mostly due to errors in the initial conditions, but perhaps also to changes in the total system energy which I didn't account for in my computational model, such as drag. Who knows, maybe Dr. Greco was blowing on the mass from the side, just to throw us off. In the graph, you can see the total change in energy in yellow, which is equal to 0. The change in kinetic energy is blue, while the changes in spring and gravitational potential energy are red and green respectively. These appear to be roughly equal in magnitude. I was pretty curious to see how bad my estimates were, so I made some graphs which plot the x and y values with respect to time for the period t from each set of Tracker data points. On the vertical axis we have our x values, while the horizontal axis is the time, t. The blue dots represent data points from Tracker, while gray are from the VPython model. As you can see, when the y values were plotted using the period from the x values, significant error resulted. The x values using the predictions for the period from the y values was slightly better, although still not great. The y values plotted with t sub y are the best, although we do see some discrepancies as the real-life model loses energy in the y direction. We saw this less markedly in the x values due to differences in the conservation of energy in a pendulum and a spring. I think the t sub x value should have given us a better estimate for the period, because the x direction was more stable with respect to energy loss, but that's not how it turned out. Both estimates for the period, 1.65 and 1.52, were very close to each other, so that may be within the margin of error for Tracker. Thanks for watching.